Let's jump right into this explainer. Today, we're demystifying anomaly detection, and we're taking it all the way from the intuitive underlying theory straight to line-by-line Python code. Honestly, whether you're hunting down financial fraud, squashing a weird bug in your system, or just trying to find that one oddball in a giant dataset, mastering this specific technique, it's an absolute game changer.
So here's our roadmap for today. We'll start with a quick intro to anomaly detection, wrap our heads around this concept of path length, prep our data, train the model, visualize the results, and then finish up with a practice task just for you.
All right, part one, intro to anomaly detection. So what exactly are we looking for here? Well, whether it's a super suspicious bank transaction that screams fraud, a weird sensor reading on a factory floor, or a visibly defective product coming off the line. An anomaly is really just a data point that looks incredibly different from the vast majority of everything else. And the key thing to remember here? This is an unsupervised learning task. We aren't spoon-feeding the model labels of what's right or wrong. We're just asking it, hey, go find what's highly unusual. Moving on to step 2, understanding path length. To pull this off, we use the isolation forest algorithm. And you can kind of think of it like a giant game of 20 questions. The algorithm basically builds random trees by randomly splitting the data. Now, if a point gets separated from the rest of the pack really quickly, meaning it has a very short path length, boom, it's highly likely to be an anomaly. It's super easy to isolate because it's just so out there. But if it takes many splits to finally separate that point, if it has a really long path length, that means it's surrounded by tons of similar points, and it's perfectly normal. Okay, part 3, prepping the penguin's data. We are going to go hunting for some unusual penguins using purely physical measurements. But to get there, we absolutely have to run through a critical 4-step data prep pipeline. Because, you can't just throw raw data at a machine learning model and expect magic. We got to prep it first. Load data, select features, drop missing values, and scale. First up, we're using pandas to slice out just the numerical features. We're grabbing things like bill length, bill depth, flipper length, and body mass. Notice we're completely ignoring the species labels. Remember, this is unsupervised learning. And then we simply drop any missing values using drop-and-na because, well, scikit-learn models literally can't train on blank spaces. They'll just break. So the big takeaway here is that our dataset is now this beautifully clean matrix of pure numbers representing those physical traits. No labels, no categories, just clean numerical data that's 100% ready for the next step. But actually, wait, we do have a slight problem. Body mass is measured in thousands of grams, right? While bill length is just a few tiny millimeters. If we leave the data exactly like this, body mass is going to completely dominate the model. It'll drown everything else out. Because of that, we absolutely must bring in a scalar standard from scikit-learn. We instantiate it, and then we fit and transform our dataset to get all these wildly different features perfectly balanced. Just look at how this transforms the data. You're no longer seeing thousands of grams or tiny millimeters. Our data is now made up of scaled values, where the mean is right around 0 and the standard deviation is close to 1. This is absolutely crucial because it ensures every single physical measurement carries the exact same weight when our isolation forest starts randomly chopping up the data. All right, section 4, training and scoring, the fun part. Now, before we even think about hitting train, we have to manually set a hyperparameter called contamination. Here, we're setting it to 0.05. This explicitly tells our model to expect that about 5% of our dataset is going to be unusual. The model doesn't magically know how many anomalies exist. We have to make that call. Out in the real world, you'd base this on business logic or domain expertise. But for our explainer today, 5% is the absolute sweet spot to help us spot those weird outliers. And here is the magic. In literally just 2 lines of code, we instantiate our isolation forest model, we pass in that 0.05 contamination rate, and we set a random state just so our results are perfectly reproducible. Then we immediately fit it to our scaled penguin measurements. Just like that, the model has built its random trees and calculated all those path lengths behind the scenes. Next, we actually ask the model to predict the anomalies using the .predict method. And to keep things super tidy, we just slap those resulting predictions in as a brand new column directly into our cleaned pandas data frame. Notice that new output column on the far right? See those ones? A 1 means a perfectly normal run-of-the-mill penguin. It took a really long path length to isolate them. But a -1, that represents our flagged anomalies. Those are the data points that were isolated incredibly quickly.
But you know, a simple binary 1 or -1 doesn't really tell the whole story, does it? To see exactly how weird our anomalies truly are, we use the decision underscore function to generate a continuous numerical score for every single row. We add that new score into our data set, and then we sort the whole thing from the lowest anomaly score to the highest. And here we go. As you can see, the smallest, most negative anomaly scores naturally float right up to the top. Scores like -0.129. These numbers represent the most physically unusual penguins in our entire dataset, at least according to the algorithm's random trees. Which brings us to section 5, visualizing the results. Looking at spreadsheets is fine, but by plotting just two of our features, let's say bill length on the x-axis against body mass on the y-axis, the model's choices just become visually striking. That huge, dense cluster of yellow dots, that's our normal majority. But look at those isolated dark purple points scattered way out on the extreme fringes. Those are the exact -1s we flagged. The algorithm perfectly identified the physical outliers, and we never even had to set a single manual threshold. Pretty cool, right?
Finally, section 6, your practice task.
So now that you've seen how this works, are you ready to try it yourself with a TIPS dataset? Can you apply this exact same Python pipeline to find the most unusual restaurant bills in an entirely new, unlabeled dataset? Here's what you need to do. Load up the TIP CSV, select the total bill, the tip amount, and the party size. Make sure you scale those numerical features, then train your isolation forest with a 0.05 contamination rate, and predict and visualize those abnormal bills. And remember, an anomaly isn't automatically a bad thing, right? It just begs the question, what fascinating story is actually hiding behind that weird data point? Happy coding!